Welcome back. In this second video, we will finish off the core material from Chapter 8 of Pre-Calculus Made Difficult, which is entitled Triangle Basics. And today we will begin with the question, which parts of a triangle are enough to determine all the rest? And to make full sense of this question, we need to unpack a few terms here, namely parts and determine. So let's begin there. Parts. Parts of a triangle. What do I mean by that? Well, here are some triangles. Obviously, these triangles have different sizes, and they have different shapes as well, meaning that they're not just all scale models of one another, the way that, say, 4 circles drawn at random would have to be. I can take any one of these circles and scale it down or scale it up, and I get one of the other ones. I'm never going to be able to simply scale this blue triangle and blow it up into this green one. They have fundamentally different shapes. Their proportions are all different. But if we wanted to quantify how these various triangles are different, what we would do is point to the 6 obvious parts of each triangle and describe those. The 6 parts being the 3 sides, in other words, how long each side is, and the 3 angles, in other words, what the numerical measurement of those angles is. At this point, measured in degrees, though later in the course we'll measure angles in a different way. So if you wanted to describe, say, this green triangle to me over the phone and I can't see it, you could do so by telling me the measurements of those 6 parts. You might say, all right, one side is 7 centimeters long, and then as we move clockwise around the triangle, starting from that side, we have an angle that is, say, 62 degrees, then a second side that's 6 centimeters long, then a second angle that's whatever specific number of degrees it may be, then the third side, which is whatever number of centimeters long it may be, and then finally the third angle, which is, again, whatever specific number of degrees that may be. And if I know those 6 parts of the triangle, I know the whole triangle. There's nothing more to say about it. Nothing more geometric to say about it, I mean. I don't care about the color in which it's drawn. But it turns out that you don't need to specify all 6 parts to determine a triangle. And by determine a triangle, I really just mean provide enough information so that there's no wiggle room left, and all the remaining parts could, in theory, be figured out. So to take a very simple example, suppose we're talking about this little blue triangle, and I only give you 5 of the parts. I tell you the lengths of all 3 sides, and I tell you 2 of the angles. Like maybe this one's 120 degrees, and this one's 25 degrees. Well, those 5 pieces of information, the 3 sides, whatever they may be, and the 2 angles, are definitely enough to determine all the rest, namely the one missing angle. Because I know from our previous video that the sum of all 3 angles in the triangle is 180 degrees. Well, these 2 angles give us a total of 145, and to bring that up to 180, we need another 35 degrees in the remaining angle. Okay, simple enough. So clearly we don't need all 6 parts to fully determine a triangle. It's obvious that once we know 2 angles, the third one comes for free, thanks to that theorem we proved in the last video that the 3 angles have to add up to 180. But it turns out that the situation is much better. We don't need all 6 to fully determine the triangle. We don't need to specify 5 to fully determine a triangle. We can usually determine a triangle by knowing only 3 of its 6 parts. That doesn't always work. It depends which parts we know. And that brings us back to our question. Which parts of a triangle, in particular, which trios of parts of a triangle will be enough to determine all the rest? And first I want to give you an example, just so we can see that yes, 3 parts can be enough to do the job, at least in many circumstances. Okay, so let's say I call you on the phone and I say, I'm describing a particular triangle to you. I'm only going to tell you 3 parts of it though. First of all, it's got a side of such and such length. So you're trying to follow along on your pad of paper and you say, okay, well, here's my side and its length is whatever. I'm going to put that one little mark there just to indicate that that's a known side. All right, that's one part. What else? And then I say, now adjacent to that side, it's got an angle of whatever measurement, 32 degrees, 107 degrees, whatever. I tell you some specific value. So on one of the endpoints, you know to mark off an angle with some specific value. And again, I'm putting that little mark there just to indicate that that's something that's known. Now you don't know how long that side is. So far anyway. I've just told you one side and then an angle connected to it. And that's clearly not enough to determine the triangle, because the triangle might look like this. That would involve the side and the angle I gave you. Or it might look like this. That would involve the side and the angle I gave you. Or it might look like this. Who knows? Clearly, there are lots of different triangles involving the side and an angle adjacent to it. Those two pieces of information are not enough to determine the triangle. But if I then give you a third piece of information, I've given you a side, an angle adjacent to it, and then I say, and then continuing around the triangle, the side that comes next is some specified length, whatever that may be, so I'll put 2 marks there, 2 just to indicate that it's different from that specified length. Once I give you that third piece of information, I hope you see that there's only one possible triangle that it could be, because all I can do is join those endpoints. There's no wiggle room left in the triangle. Those 3 pieces of information completely determine the triangle. Wait just a second. I am breaking in on myself to clear something up that might otherwise be confusing. I just claimed that side angle side is enough to completely determine a triangle. And my justification seemed simple enough. We have a side, then an angle, then a side, and then of course, there's only one way to complete that triangle, right? Well, yes, but I'm imagining that some people watching this video might have thought, well, wait a second. If all I know are the 3 numbers, the length of one side, the measurement of an angle adjacent to it, and the length of the side on the other side of that angle, those 3 numbers don't tell me whether the angle goes on one side of the line segment or the other, nor does it tell me whether it comes off of one endpoint of the line segment or the other. Might those choices make a difference? It's a very good question. And the answer is no, it really won't make a difference. But I want to draw some pictures just to reassure you, because it's a good question, as I said. So in the original way I set this up, we ended up with this triangle right here. But suppose we had put the angle going the other direction. Then our triangle would have looked like whatever we get out of this. In other words, we would join those last 2 vertices up, like so, and we would have this triangle. And although my drawing is terrible, I hope you can see that these really are 2 copies of the same triangle. The only difference being that we're looking at different sides, as it were, to the triangle. I don't mean the sides like the edges. I mean, like if you imagine our original triangle as being cut out of paper, it's like we took the piece of paper, the triangle-shaped paper, pulled it up out of the plane on which I'm drawing, turned it over, and plopped it back down so that its underside was showing. Maybe the most direct way to see this is by imagining what would happen if we took this line right here and extended it and thought of it as a mirror. The 2 triangles are now just mirror images of one another. In our original one, we encountered the first given side, then the angle, then the second given side by going counterclockwise around the triangle. And in the second one, we encounter the first given side, the angle, and the second given side by going clockwise around the triangle. But it's still really the same triangle. It's just being seen from 2 different perspectives. As I said, these 2 instances of the triangle can just be thought of as reflections of one another. If you really want to drive this point home for yourself, just get out a sheet of paper, draw a triangle, label a side, an angle, and then the next side. Do it whichever way you want. Like in this one, I drew it going counterclockwise around the triangle, starting on the side with 1 stroke and ending on the side with 2 strokes. But anyway, take the piece of paper that you drew it on and go hold it up to a mirror. And you will see that in the mirror image, if you follow those same sides and angles in the same order, the one with the 1 stroke, the angle, and then the one with the 2 strokes, in the mirror image, through the looking glass, you will be going not counterclockwise, but clockwise. Or if the first one was clockwise, then you'll be going counterclockwise. But it's still the exact same triangle. You're just seeing it from a different perspective. The moral of the story being, it doesn't matter whether we drew the angle here or here. We still get the same shape and size of triangle, even if it's a mirror reflection of it. Same story happens if we had put the angle at the other endpoint of our original line segment. So for example, if instead of putting it down here, we had put it up here, exact same angle size, just on the other endpoint. So then we have side, angle, and then I'd have to extend that to that same length with the 2 strokes, and then complete the triangle by connecting those 2 endpoints. And the triangle that we obtain, once again, really is identical to the original triangle that we started with. It's another mirror image of it. In fact, you could see right here that it's being flipped over a line like that. If we took our original triangle and reflected it over that dotted line, what we would get would be exactly this triangle right there. all the same sides, all the same angles. It's just like we took this original triangle, lifted it up out of the page, turned it over so its underbelly was exposed, and put it back down on the page. So it's flipped over, but it's still the same triangle. Same size, same shape. And I'm not going to belabor the point, but of course the same thing is true if we had tacked the angle on this endpoint, but coming off this other direction. We'd still get the same triangle. Same size, same shape. Okay, that's enough for my interruption. Maybe for one or two viewers out there, this put your mind at ease. I'll now return to my very slightly younger self, who has no idea he's being interrupted. Take it away, younger self. And you might reasonably object, well, sure, it determines it in one sense, but I still don't know the measurement of that third side or those two angles. And that's true. That's fine. We will learn in the coming chapters how to actually find those measurements. What we're interested in here is just the question, which parts are enough to nail down the one triangle uniquely? If I know those three parts, two sides and the angle in between them, that's enough to do it. Because what we will see is, once we have enough information to fully determine a triangle, then the subject that we are developing, trigonometry, will handle the rest. In the book, I describe it as a trigonometry machine that we are going to build in the coming chapters. And the way it's going to work, once we have enough parts of a triangle to determine it, in theory, like we have here, our two sides and the included angle, we feed that information into our trigonometry machine, and it will be able to produce the numerical values for all the remaining parts. What we are learning right now is the circumstances under which the trigonometry machine will be an effective tool, because we don't just want to learn how to operate the tool. We want to know when it is an appropriate tool. And it will be appropriate precisely when we have enough parts of a triangle to determine its size and shape, which we do here when we have two sides and the included angle. And our first project in this video is going to be to run through all the possible trios from among the 6 parts of a triangle and figure out which trios are enough to determine the entire triangle and which ones are not. So let's make a few little lists here. Let's begin with all the possible trios. There's not that many to begin with. Possible trios of triangle parts. We've just discussed one. Two sides and the included angle, the angle between them. So I am going to label that scenario SAS for side, angle, side. Two sides and the angle in between them. And what we've shown is that if I have a situation like that, that's enough to determine the whole triangle. Okay, so that's one possible trio. What are some other ones we have to think of? Well, let's see. What if we had two sides and an angle, but the angle wasn't in between them? So we knew two sides and then the angle, or the angle and then the two sides. So something like ass. Is ass enough? We'll get to that question in a moment. Oh, and by the way, you might say, oh, and don't forget SSA, side-side angle. Well, these are really the same thing. It's just a matter of perspective. I mean, if we're looking at some triangle, and I point to these 3 known parts and say, angle, side, side, ass, and you look at the same thing and just look at it in the opposite direction, side, side, angle, sa, it's the same thing. We don't care about which order we're going around so we don't have to worry about SSA. It's the same thing as ASS. So I will erase that. For now, let's just continue listing all the possible trios. So those are the only possible trios where we have two sides and an angle. Either the angle is in between or it's not. Okay, well, we could also have a trio where we have two angles and a side, and we have the same possibilities. The angles could be surrounding the side, ASA, or it could be two angles and then the side, or if you like, the side and then the two angles. It's the same thing, because it doesn't matter whether we're reading it this way or that way, so I will only include that once. Great, so these are the only possibilities where we have two sides and an angle. These are the only possibilities where we have two angles and a side. Well, we're almost done. The only other trios that would remain would be if we had all three sides or all three angles. And that's it. That's the complete list of possible trios of triangle parts. So these are our candidates that we have to consider. Consider each one and see whether it's enough to determine a triangle, like side, angle, side, or if it's not. So let's just go down the list. So next on the agenda, let's talk ass. So let's say we know angle in a triangle, and then a side adjacent to that angle, and then another side adjacent to the given side. We know its length, but we don't know exactly where it is because we're not told that angle. So let's just imagine that that second side is just hanging loose here. Like we could imagine rotating it around on this thing. We know its length, but we don't know exactly where its endpoint is going to lie on that circle. Now we see the problem, because if we spin that thing around, well, it could hit this side of the triangle, whose measurement we know nothing about, in two different places. It could hit over here, which would give us this triangle, or it could hit it over here, which would give us this triangle. And notice the problem. On this inner yellow triangle, we have the given angle, A, then a side, S, and then another side, S, coming in that order. But on the bigger outer triangle, the purple triangle, we have the exact same angle, side, side going around the triangle, which means that ASS, angle, side, side, is not enough to determine a triangle. Given that information, angle, side, side, or if you want to read it the other way, side, side, angle, that's not enough information to nail down precisely the size and shape of a triangle, because these two triangles are very different, even though they agree on those three parts in that particular order. So ASS is definitely not enough to determine a triangle. There is real ambiguity as to which of these triangles is meant. Because of that ambiguity, I think of this trio as the ambiguous ASS, which if nothing else makes it very easy to remember that ASS is not enough to determine a triangle. All right, let's continue down the list. ASA, two angles and the included side. So that would be something like this. We know two angles, we know the length of the side between them, but we don't know anything about the lengths of the sides on the other side. Is ASA enough to determine the triangle? Well, in this case, it's very obvious, very much like the side angle side. There's only one way to continue those lines. We continue them up until they intersect, and that's going to be the third vertex of the triangle, and the triangle is completely determined. So that means ASA is indeed enough to do the job. If you know two angles in a triangle and the side in between them, clearly there's only one triangle that your triangle could be. I mean, one shape and size of triangle. We're not interested in the location of the triangle in the plane or the color of the triangle or anything like that. But its shape and size are completely determined by knowing two angles and the side in between them. This is quite obvious. And what this is going to tell us is that once we build our trigonometry machine, we'll be able to identify, here's a triangle and I know two angles and their included side. Let me throw those three pieces of information into the trigonometry machine, and it will tell me what the measurements of the remaining two sides and the remaining angle must be. You'll have to wait for us to develop that machine before we can carry out the details. As I say, for now, we're just trying to figure out when the machine will be the appropriate tool. Excellent. Next up at the plate, angle, angle, side. Well, let's think it through geometrically. That would look something like this. We'd have an angle, but I wouldn't know the lengths of the sides around it. And then the next piece of information I would know would be another angle, but I don't know how far away it would be. So I know that angle's measurement, but I'll leave some dots here because I don't know if it's nearby this first one or very far down the road. So angle, angle clearly isn't enough to tell me what's going on. But when I throw that third side in, let me just draw a specific length in, maybe something like that. So that's a known side. That will be enough to nail down what the triangle has to look like. Clearly it doesn't look like this because that's not a triangle. But remember what's going on. I don't know this distance right here. I know that angle and I know this length. So I have to consider the possibility that it could be much further away or much closer. So imagine taking this little piece and sliding it up and down this until everything fits. And there's only going to be one position where it does. Like if I slid this thing a little bit this way, well, that's clearly not going to be any help because I'd end up with something like that. And if I slid this thing too far down that way, well, I might end up with something like that, but that's not going to work either because this point isn't going to lie on that line, which I know contains my third vertex of the triangle. So in fact, let me just extend that line that I know must contain the missing vertex. And let's slide this back and just imagine what happens as we do. We get closer and closer and closer, and at just the right distance, it fits perfectly. If we go further beyond that, we overshoot it. If we don't get that far, we undershoot it. But at that one and only that one position, everything fits nicely. And consequently, that determines the only possible triangle we could be considering here. The only one where we have the angle, and then the side. Or if you want to read it backwards, the side, the angle, and then the angle. But at any rate, two angles and a side that is not included between those angles. So angle, angle, side does the job. That is enough to determine a triangle completely. Good. By the way, that's not the only way to to see that angle, angle, side will do the job. I wanted you to get a feel for it, a tangible feel for it geometrically. But there's an even faster way to see it, which I describe in the book. Namely, if we know two angles and the non-included side, well, don't forget the lesson of the previous video. If we know two angles in a triangle, of course we know all three angles because the three angles have to add up to 180. And if we know three angles and a side, well, of course the side lies between two of the known angles because all three angles are known. So that means angle, angle, side immediately gives us angle, side, angle. And we already knew that angle, side, angle does the job. And so angle, angle, side gets the coveted check mark. Two ways of seeing the same thing, each bringing with it its own peculiar insight, which is what we want in mathematics. We want to be able to see the same thing from multiple angles, learn something new each time. All right, we're on a roll. We've taken care of all the cases where we have two of one kind of part and one of the other. Now we have to consider the ones where we have three of a kind. So next up, side, side, side. Is that trio enough to determine a triangle? Well, let's see. Suppose I tell you that I have a triangle and it's got a side of length A and then a side of length B and then a side of length C as we go around. Is that enough to determine the rest? Is that enough in particular to determine the angles? Well, let's think about it. Let's start with our side A. And then we know as we go around that we have some side length B coming off of its endpoint, but I don't know at what angle. I just know that sides A and B are joined at this vertex. So for now, let me just put side B like this, just continuing on in a straight line. We'll figure out exactly where that endpoint should be in a moment. And then we know we have a side of some specified length C coming out of this endpoint. So maybe something like this. Well, think of these vertices as hinges around which I can rotate sides A and C. That means this vertex could end up on this circle centered at this vertex and with radius A. As I swing that point around, and I can rotate side A into all the different positions in which it might be. Okay, but I'm also doing the same by rotating this side, side C around, which means that this vertex is going to end up somewhere on this circle. I could rotate it into this position, or this position, or this position, or this position, or whatever. But as we can see, there are only two very special positions, namely this one and this one, that lie on both circles. Those are the only points where I can get my third vertex. If this is the first vertex of my triangle, and this is the second, this is the only place, this or this, where I can get a third vertex so that everything fits, so that my three pieces actually fit together to create a triangle with one side of length A, another side of length B, and a third side of length C. Notice there are two possible triangles, either this one up here with side lengths A, B, and C, or this one down here with side lengths A, B, and C. Those are the only two possibilities, but it's also true that it's really just one possibility because those two triangles are the same triangle. Once again, they're just mirror images of one another. Obviously, they have the same angles. This angle right here matches this angle. This angle up here matches this angle. And this angle over here matches that angle. If we had this triangle cut out of cardboard or something, and we lifted it up out of the plane and flipped it over, exposing its underbelly, and put it back down, it would look like this. So it's the same triangle. And that's the only way to get a triangle from side, side, side. So that means that we have the answer to our question. Yes, it is enough to determine a triangle, which means that once we have built our gleaming trigonometry machine, if you give me the three sides to a triangle, I will be able to stick those in the trigonometry machine and produce the values of the three angles. We see here that they are definitely determined, but what their numerical values would be, given the numerical values of the sides, is something that our trigonometry machine will allow us to find. And look at that. We have only one more to go. Angle, angle, angle. Open up and say, is angle, angle, angle enough to determine a triangle? If I tell you the three angles of a triangle, should that be enough for you to tell me what the three sides must be? Well, just a few seconds of thought should tell you that this is definitely not enough to determine a triangle. After all, suppose I have a small triangle in which the angles are all equal, 60 degrees, 60 degrees, and 60 degrees, so that they add up to 180. Now, imagine just blowing this thing up on a photocopier so that I have a large triangle whose angles are all 60 degrees. Well, these two triangles agree on angle, angle, angle. They have all the same angles, but they're totally different triangles. I mean, they have the same shape. They're both equilateral triangles, but they have completely different sizes. I could have one where each side is a millimeter and another where each side is a mile. We'll see very soon that angle, angle, angle is enough to determine the shape of the triangle, but it is not enough to determine its size. So these two are proportionate, but they're not the same triangle. They're on a very different scale. And with that, we have finished running through all the possibilities for a known trio of parts. You should know which trios are enough to determine a triangle and which ones are not enough. And you might think, oh, that's a lot to remember. It really isn't, because all you have to do is remember the ones that don't work, since there's only two possibilities here. And the ones that don't work are very easy to remember. Everybody remembers that the ambiguous as is not enough to determine a triangle. It's ambiguous after all. And everybody remembers that angle, angle, angle isn't enough to do the job. Just think of two equilateral triangles of vastly different sizes. So that's all you have to remember. The ambiguous as won't do it, and neither will angle, angle, angle. Every other possible trio of parts is enough to determine a triangle. I should mention one special case of the ambiguous as, in which the ambiguity disappears. If you have not just as, but RASS. RASS, you say. What is RASS? That's right angle side side. If we have RASS, then as I say, the ambiguity in the ambiguous as disappears, and RASS is enough to determine a triangle. Why is that? It's very easy to see. Suppose we have a right triangle, right? Because we've got a right angle in it. So we have our right angle, and then we have two sides. Well, if I have two sides of a right triangle, Pythagoras immediately tells us what the third side is. So we get the third side for free, thanks to the Pythagorean Theorem. And that means that if we have right angle side side, then we also have side angle side. And that is the first and most obvious determining trio. So yes, RASS does the job very nicely, and recognizing that sometimes comes in handy. In fact, the ambiguity in the ambiguous as really only occurs when the angle is an acute angle. If it's obtuse, the ambiguity disappears as well, but for a different reason, and it's not important enough for us to dwell on here. This is the key stuff, and I thought I would just mention RASS in passing. All right, now I want to describe a scenario where knowing this kind of stuff helps us even before we know how to operate the trigonometry machine. It's going to help us identify, aha, this is a situation where the trigonometry machine will be effective. And at this point, you can call in your friend who knows how to operate it. Very soon, you'll be able to do it on your own. So, suppose we have a setup like this, where we have several triangles all touching one another, and we know certain parts of the triangles. Like I know this side that has the one stroke, and this side that has the two strokes, and this side of this other triangle that has three strokes, and this side of a different triangle still that has the one wavy stroke, and this one that has the two wavy strokes. But I don't know this side or this side or this side. And then I know a couple of angles. I know this angle, which I've labeled alpha, and then in this other triangle I know this angle, which I've labeled beta. And let's say that we want to know this angle, where I put a question mark. And you might say, that's a strange setup. How might something like that arise? Well, think back to what I said in the previous video, that any polygon whatsoever can be triangulated, chopped up into triangles. So what I'm looking at here might be part of some larger polygon that we're interested in for whatever reason. To take a very classical example, maybe it has something to do with land surveying, but whatever. My question is, do we have enough information, given the weird assortment of angles and sides that we know in this picture, to find this angle that we desire? Assume that the trigonometry machine is waiting in the wings. We just have to decide whether it will do the job for us. We don't have to know how to operate it yet. That will come in good time. Well, let's think our way through this. The first thing you might note is, well, the angle we want is a piece of this triangle. Do I have enough information to determine that triangle? Well, I know two sides of that triangle. But that's all I seem to know. Two pieces of information is not enough to determine a triangle. Oh well. Hey, but wait. Maybe I can get some information, because this triangle shares this side with another triangle. So if I know enough information to determine this triangle, I could get that side, and then I'd have side, side, side. That would determine this triangle, and that means I could get this angle using our trigonometry machine. Do I have enough information to determine this triangle? Well, let's see. I have one side and one angle. Damn, that's not quite enough. Still only two pieces of information. Hey, but wait. This triangle has an angle in it which we know is equal to this angle over here. Those are so-called vertical angles, not meaning vertical like standing straight up, vertical as in on opposite sides of a vertex. And we know vertical angles are equal, as I mentioned earlier in the book. That means if I could figure out what this angle was in that first triangle, then I would know what this angle was. So I'd have angle, side, angle. That would determine this triangle. Then I would be able to get that side using the trigonometry machine. And then I would have side, side, side on this triangle so I could get the angle I want. But I don't know what that angle is, so I can't set that chain reaction in motion. But I can figure it out, because on this first triangle over here, I do have enough to determine this triangle. I have side, angle, side. That's enough to determine this triangle, so I can call in the trigonometry machine, tell the person operating it, this triangle is determined. Find for me this angle right here, and he'll be able to do it. And then you'll know that that angle is equal to this angle, since those are vertical angles. And then you can say, now this triangle is determined, because we have angle, side, angle, which is one of our determining trios. Use the trigonometry machine to find out this side, and you'll be able to do that. And then you can triumphantly declare, and now this triangle is determined, because we have side, 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 another one of our determining trios. You there, take that trigonometry machine and use it to find this angle, and then you can do just that. And the problem is solved. So with a little bit of thought, we can go from the information we were given all the way to the end of the problem. We recognize exactly what the path is to find a solution. Once, of course, we know the basics of trigonometry, which we're going to be learning soon enough. Good. I should mention a little vocabulary with which you are probably already familiar from a geometry course or something like that. These determining trios that we discovered, side, angle, side, angle, side, angle, 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 side, and side, side, side. You may know them already, and certainly if you've been reading the book, as congruence criteria. So let me import those four over here. When we were talking about determining a triangle, having enough information to nail down both the shape and the size of the triangle, the fancy term for triangles that are equal in that sense, triangles that have the same shape and the same size, are congruent triangles. So these two triangles appear to be congruent, while neither of them is congruent to that triangle. How do you know whether a pair of triangles are congruent? Well, if they agree on one of these various congruence criteria, then they're congruent. Like if you knew that these two triangles have those angles equal, and these sides equal, and these angles equal, then you could say, we now have enough information to declare that these triangles are the same, or rather, that these triangles are congruent, so that all of their corresponding parts are equal. These things operate as congruence criteria because if two triangles both have the same side, angle, side, they're both determined in exactly the same way. So of course, they're the same triangle. And for that matter, I could add to the congruence criteria RASS, right angle, side, side. So going back to our original list, we've said everything we need to about the various congruence criteria, and we've even noted that the ambiguous AS, in one special case, is not ambiguous at all, and RASS is a congruence criterion. But is there anything left to say about angle, angle, angle? I hinted at this earlier, and now is the time to discuss it more fully, because it's going to be very important to us in the next chapter, even though it is not enough to determine a triangle. It still tells us something important about a triangle. And in fact, angle, angle, angle could be whittled down to simply angle, angle. Because if I know two angles of a triangle, of course, I automatically know the third angle because I know the three have to add up to 180. So the missing angle is whatever brings the total up to 180. So it's really a matter of overkill to talk about angle, angle, angle. Let's just cut it down to its basics. If we know two angles in a triangle, and therefore we know three angles, what does that tell us about the triangle? Well, to get a feel for this, let's just use the things I've already scribbled on the board here. I don't need two copies of it, so I'll get rid of one, and let me get rid of this side. Let's just say I have a triangle where I know two angles. Of course, it determines the third angle, as we said. What does it tell us about the triangle? I claim that angle is enough to tell us the shape of the triangle. It won't tell us how long the sides are, but it will tell us the ratios of those sides. It won't give us a congruence criterion, but we will know that if we have two different triangles that share two angles, those triangles will at least have the same shape, even if they are very different sizes. They will be what we call similar triangles, as I'm sure you know from previous courses. And let me try to explain, at least roughly, why that is so. Okay, so let's say I have some other triangle that shares these angles. I don't know the side in between them, so maybe it's much larger or much smaller. I'll draw it much larger. And then we have this same angle here. I'm trying to draw it as best I can. And this same smaller angle over here. Look at these two triangles that agree on angle. Do you see how I could take one and blow it up to get the other one? Or take the larger one and shrink it down to get the smaller one? They have the same shape, and you can see this a little more carefully by just trying to match up their parts. Like, let's take the smaller one. If I wanted to move it so that this vertex matched up with this vertex, and this side lay on top of this side, then I hope you see that this other side would also lay on top of this side. That's because those angles match up. So if I move this one down here, it would have to look something like, I'll put it in a different color so we can talk about both of them simultaneously. It would have to look something like this. And of course, whatever this third angle was, which is still here when I moved it, that's going to be the same as this angle up here, because the three angles, of course, have to add up to 180 degrees. So if 1 stroke plus 2 strokes plus the solid white is 180, well, the 1 stroke plus the 2 strokes is going to need a solid white to bring it up to 180 in this other triangle. But notice the way this works out. Now we have this line right here and this line right here. They are departing from this line at the same angle. That means they are going to be parallel. And as you might remember from an earlier geometry course, and even if you don't, it's very intuitive. If you have a triangle and you take a point on one side and draw a line coming from it so that it's parallel to a side of the triangle, then the two triangles you end up with, the original triangle and the smaller one, are just scale models of one another. You could blow up the small triangle by a certain factor and get the big one, or take the big one and shrink it down by a certain factor and you get the small one. They are so-called similar triangles. Same shape, just different sizes. Well, that's what we have right here. Our two triangles, this large one and this smaller one that we started off with, just noting that they had two angles in common, they turn out to be, as is very intuitive, similar triangles. Same shape, different sizes. To get from one to the other, you just scale all the linear dimensions by some factor. For example, let's just say in this case, this side length was, 3 units, and on the larger triangle, the corresponding side length was maybe 7 units. Well, from that, we can read off the scaling factor. To get from 3 to 7, what do we have to multiply by? Of course, we have to multiply by 7/3. 3 times 7/3 is 7. So that's going to be the same scaling factor to get from any of the sides to any of the other sides. So if, for example, this side of the smaller triangle is, say, 8 units, then what's the length of the corresponding side on the larger triangle? Well, we just have to multiply by the scaling factor of 7/3. So we would get 56/3 would be the length of that larger side. Fairly straightforward. And maybe I should write this in a different way that will help pave the way towards what we'll do a little bit in the next chapter. Let me keep the same basic pictures, but I've removed lots of the stuff we don't need. Okay, these two triangles agree on angle. Well, angle is an example of what we would call a similarity criterion. So let me shift that up there. When two triangles agree on angle, they are similar triangles. So as we said, all their proportions are the same. Now we figured out this side a minute ago by thinking about the scaling factor, the linear scaling factor. We had to multiply all the sides by 7/3. But an equivalent way to do that is to say, well, what is this big question mark? What you might have done in a geometry class is actually set up a little proportion. You might have said, well, whatever this question mark is, that question mark is to 7. So the ratio of this side to this side is the same as the corresponding ratio on this triangle, which of course would be 8 to 3. And of course, when you solve that for the question mark by multiplying both sides by 7, you end up with the question mark being equal to 56/3, which is of course what we saw before. We were able to set up this proportion, this equality of ratios, because we knew these two triangles were similar, because they agreed on angle-angle. And angle-angle is our key similarity criterion. There are other similarity criteria out there, but this is the only one we're really going to need in this course. And it's going to make all sorts of important things happen when we get to the next chapter. In particular, if we look ahead a bit, just for a moment, let's consider two right triangles in particular. That's what we're going to be dealing with in chapter 9 exclusively. And let's say these two right triangles are known to have another angle in common. For the sake of argument, let's just say it is 39 degrees. Okay, then these two triangles agree on angle-angle. They both have a 39-degree angle, they both have a 90-degree angle. That means that these two triangles are going to be similar. That means that all their corresponding ratios are going to be equal. For example, even though the corresponding sides will be different, like clearly this side over here is longer than this side right here, whatever the ratio is of this side to this side on the smaller triangle will be the exact same ratio as this same side to this same side on the other triangle. And similarly, whatever this hypotenuse is to this long leg is, that ratio will be the same as the ratio of the hypotenuse to this long leg over here. And it will be the same on any triangle in the universe that has a right angle and a 39-degree angle. Those ratios will be what we come to know as the trigonometric ratios, but more on that to come. For now, we're just laying the foundations. And I think I'm going to finish this one off by showing you another proof of the Pythagorean theorem. I do this one in the book as well, but let me talk you through it here because it's a very nice application of similar triangles. So let's say we have a right triangle, and let's call its legs A and B, and its hypotenuse C. I want to prove that c squared is equal to a squared plus b squared. In the last video, we saw Euclid's beautiful proof of this fact. Here I'm going to use another really nice proof. What I'm going to do is I'm going to start at the right angle here and drop a perpendicular to the hypotenuse. And the foot of that perpendicular cuts the hypotenuse into two pieces. And I'm going to call those two pieces C1 and C2, so that C, the full hypotenuse, is just the sum of C1 and C2. Now here's something interesting. When I dropped that perpendicular, I chopped our original right triangle into two smaller right triangles. So I actually have three right triangles here, the original and each of the two smaller ones. A little bit of thought should convince you that all three triangles are similar to one another. They're all just scale models of one another. For example, let's concentrate on this angle right here. I will just call it the purple angle. Now that purple angle belongs to two of the triangles, two of the right triangles. It belongs to this little one on the left, and it belongs to the original triangle. So the little one on the left has the purple angle and a right angle, and the original triangle has a purple angle and a right angle. So that means the little one on the left is similar to the original by angle-angle similarity criterion. Well, guess what? If we take this other angle over here, and I guess I will call that one the yellow angle, well, this yellow angle belongs to the right triangle on the right, and it belongs to the original large right triangle. So the right triangle on the right has a yellow angle and a right angle, whereas the original large triangle has a yellow angle and a right angle. That means the triangle on the right is similar to the large, which in turn is similar to the triangle on the left. Since both of the smaller right triangles are similar to the original, they're also similar to one another. All three of those triangles are similar. They're all just scale models of one another. That means that all their corresponding ratios are equal. I think that's pretty neat in and of itself, because that means you could start with any right triangle, drop a perpendicular, get two new right triangles, both of which are similar to the original and to each other. Then you could do the same thing on the smaller triangles, right? Drop perpendiculars from their right angles, and all the triangles in this picture are similar to one another. And of course, you could keep doing it till the cows come home. And again, my picture is looking terrible, but you get the idea. There's no end to this process. You could get triangles as small as you like, and everything you produce all the way out, hundreds, thousands, millions of times, they will all be similar to one another and to the original triangle. Neat, but that's not what I want to talk about here. We are trying to prove the Pythagorean theorem, and this interesting property will help us, I claim. Okay, why? So I know these three triangles are all similar to one another. That means that if I look at the ratio A to C1, that is, on the left triangle, the hypotenuse over the leg that is adjacent to the purple angle. By the similarity of that left triangle to the original big triangle, I know that that ratio of hypotenuse to the leg adjacent to purple is going to be the same, thanks to similarity, as the same ratio on the original triangle. That's hypotenuse, which is C, over the leg adjacent to purple, which is A in that case. So A is to C1 as C is to A. Well, thanks to the similarity of the small triangle on the right and the original triangle, I get another ratio that I'm interested in. I'm going to look at the ratio B to C2. So let me write that down here. That's the hypotenuse to the leg adjacent to yellow. Well, that's going to be equal to the corresponding ratio on the original triangle. Hypotenuse, C, to the leg adjacent to yellow. That's B. So B is to C2 as C is to B. So just to be clear, we got those two equalities by similar triangles. All right, so we understand that that's true, but so what? Well, let's do a little algebra. From this first proportion, I am going to extract a new equation by clearing the fractions here. And when I do that, I get a squared is c times c1. Easy enough. And now I'm going to do the same from this second proportion. Clearing the fractions, I get b squared is c2. Hey, well, that's pretty interesting because now I have an expression for a squared and b squared, which are two of the things I'm interested in the Pythagorean theorem. Well, in that case, let's see what happens when I add a squared and b squared together. According to these two equations, adding a squared and b squared is the same thing as adding cc1 and cc2. But seeing that expression, all your algebraic instincts should kick in and you should have an irresistible urge to factor out that common factor of c, giving us c times the quantity c1 plus c2. Hey, and what is c1 plus c2? Here's c1 and there is c2. Add them together and you get c. So this becomes c times c, better known as c squared. So what have we shown? A squared plus b squared is c squared, when a and b are the legs of any right triangle and c is the hypotenuse. And our proof of the Pythagorean theorem is complete. All right, that's a very pretty little proof. And you should consider of the various proofs you've seen of the Pythagorean theorem. Do you have a favorite? And why? You can compare them aesthetically, the way you would compare two pieces of music or two movies or whatever it might be. You can enjoy them both, but for different reasons. This one I like because it's so self-contained. You just draw that one perpendicular and similarity takes care of the rest. But on the other hand, the algebra sort of takes us away from direct intuition. The argument in Euclid's proof, which I showed you in the previous video, is more complicated, but I like that it keeps the geometry front and center the whole time. You may feel differently. That's okay. Different strokes for different folks. But you do want to be developing an aesthetic sense for mathematics, an appreciation of it as an art as you go through these courses that you're taking. If you're thinking of it as just a bunch of algorithms that you memorize, you're not thinking of the subject in the right way. And you probably, frankly, won't get that much out of it. So don't do that. It's a great subject. Get everything you can out of it. It's excellent for all sorts of practical reasons, and it helps you attain a higher intellectual level in general, which is a good in and of itself. All right, well, it's hard to think of a better note to end on than a pretty proof of the Pythagorean theorem, so I will stop there. And next time, we will start chapter 9. Until then, goodbye.